All right, so if you have not gotten completely bored and dead from the other two videos, I promise you this one will be a little bit quicker and more succinct and to the point, because this kind of circuit analysis is a little bit easier. If you're a math type, basically all we're doing is we're building simultaneous sets of equations for circuits. I mean, literally that's all we're going to do. There's no redrawing the circuit. There's no compressing it. There's no having to run back through it to find all the currents. One of the things you will be doing, however, is making some assumptions. And what Kirchhoff's rules are, there are basically two of them. And you actually kind of know these already. But the first one is known as the junction rule, or the node rule, node or junction, depending upon who your instructor is. And basically what the node or junction rule says, simply put, here's the mathematical version of it, it's that the current into a junction is equal to the current out. And that's what you've been doing all along. Every time we came to a node, we said, okay, if there's current coming this way, it splits and goes here, and it goes here, and these two guys have to add back up to that. So it's really nothing new. It's just a restatement of stuff that you've been seeing. The other rule he has looks like this, and it's often referred to as the loop rule. What the loop rule is, again, pretty much what we've already said. It says when you go around a loop, when you go around a series circuit as an example, it tells you that the voltage that you put in has to equal the voltage that is used by the resistors. It's that simple. Now the voltage that is used by the resistors, we're going to call it I times R. In other words, you're using Ohm's law. Or if you really want to get heady with this, we're talking about conservation of energy. We're saying whatever energy you put in has to be used by those resistors. And if we're really talking heady about the node rule, it's conservation of charge. Whatever charge that goes in has to come out. So it's just a restatement of those things that we've seen already. So let's take a very simple circuit, and it's literally the first one that I did on the other circuit. It should look vaguely familiar. It's the same one that I started with you before. Okay, so one of the first things we need to do is we need to use the junction rule. And there's a junction here. Oop, let me change color so you can see it. There we go. There's a junction here. And that junction seems to come back together here. Now, what you tend to do when you do these kind of Kirchhoff's laws is you look at the battery and you try to find the biggest battery you can, and you start on the positive side of the battery. So as I come around here, there's going to be current flowing through that 25 ohm. It's going to come here and split. So I'm going to call this current I1, the one that's flowing through the 25. When that hits here, it's going to split. Some of it's going to go that way. Some of it's going to go that way. I'm going to call this current I2, and I'm going to call this current, go figure, I3. When those guys all come back together, they're going to remake I1 again, so that means that I1 is going back through the 50 ohm, and then it goes back to the battery. So right away we can see that we have an equation. I1 is equal to I2 plus I3. Now, first thing I want you to notice is there are three variables. And you know from your math background that if you have three variables, you're going to need three equations to solve it, right? So that equation came out of the junction or the node rule. The other two equations are going to come out of, you got it, the loop rule. We're going to look at the voltages. Now, the only rule really about the loop rule is that when you draw your loops, you want to cover all the elements in the circuit. And if you can't do it with one loop, then you're going to have to use a second loop. And if you can't do it with a second loop, maybe you even need to do a third loop. The way that I look at it is I look at a circuit and I look for like a honeycomb. I look for cells. So there's a big cell right here. And then there's a smaller cell right here. So I tend to make my loops where the cells are. So I'm going to show you my first loop. Here's the first loop. Comes to the junction. I'm going to take this path. I'm going to follow it around, and I'm going to go back to the battery. And I'm going to call that loop number 1. Right? There's my first loop. Now what you're going to notice is I've got this 100 ohm resistor hanging out over here that doesn't have anything, a loop going through it. That's a problem. That means I'm going to have to at least have a second loop. Let me show you what I'm going to do for my second. Well, let me do the first loop first. Let me actually do the math with it, and then we'll come back and look at the second loop. So let's look at the math. Remember, it says whatever voltage you put in has to equal the resistance, the voltage that the resistors use. So I start with my battery. I've got 1.5 volts. Right, so there's the voltage in. Now as I start to follow my loop around, I come to here. Well, what current? That's I1. So I'm going to say I1 times 25 ohms. Still following my red line now. I got that resistor done. Come up through here. Here we go. I've got plus I2, because that's what my current is in this one that I called it, times 100. Afraid I'm going to run out of room here. Ohms. I follow my red line around, and I come around to here. So I'm going to say plus I, and remember, these came back together, so that's I1 times 50 ohms. So now I've got my second equation. So I'm going to clean it up a little bit, and I'm going to do the unthink of and drop my units just so you can see this very quickly. So I've got 1.5 on this side, and I've got 25 I1 plus 50 I1, so that's 75 I1. And then I've got plus 100 I2. All right, so I've got my variables I1 and I2 out of that loop equation. But I'm still needing one more loop because there's a sneaky little I3 up here. There's that third variable. Let me get a different color here so you can track what I'm going to do. Let me get one that you can follow. Let's go blue, I guess. All right, so you need to draw another loop. Now here's the thing that bothered your classmates but shouldn't bother you. All the loop rule says is whatever voltage you put in has to equal to the voltage that is used, right? So here's what I'm going to do. I'm going to make my second loop this loop right here. I know what you're thinking. You're saying, but wait, you didn't include a battery. Doesn't matter. It does not matter. Let's apply the voltage rule. So if you don't see a battery in here, guess what you start with? Oh, there's no battery. There's 0 volts equal to whatever's being used. Remember, these aren't real circuit paths. These are imaginary paths that we're making up so that we can solve our equations. And the cool thing is, if you choose poorly, oh, guess what? It's going to tell you, and it's going to give you a negative answer. We'll talk about that in a minute. All right, so here we go. If we follow the circuit around, I got I3 times 100 ohms. Well, that's pretty easy. I follow this blue line around, and I come over here to this other resistor. But what I need you to notice is it's going against the direction of I2. The way that you tell your equation that is by putting a negative sign there. So you would have negative I2 times 100 ohms. I come back around and I'm back to where I started. There's my other equation. And this one's a pretty nice one because if you look at it with nothing over here, that's pretty cool. And you also notice that I've got 100 I3 and I've got 100 I2. So very quickly, if you do just a little bit of rearranging, you can see that I2 is the same as I3. Shouldn't be a shocker because if you recall last time when I showed you, the current comes into here, and since these resistors are the same, the current splits evenly. So this even verifies further what we had talked about before. Now your game is real simple. You have 1, 2, 3 equations to play around with and get something to fall out. All right, well this one's kind of useful because it tells me that I3 is the same as I2, so I can rewrite it this way. I2 plus I2. Well, that's make it even nicer because that means I1 is equal to 2 I2. And I can now take this and substitute it right there. So now my equation becomes 1.5 is equal to 75 times 2I2 plus 100 I2. That's a very solvable equation. I've got 1.5 is equal to 150 plus 100 is 250, I2. So now you literally get an answer for I2. It's going to be 1.5 divided by 250. And I think, if I'm not mistaken, it should come out to be something like 0.006 amps. So, what does that do for you? Well, that also gives you another answer, because you know I2 is the same as I3. So that means there's 0.006 amps here. There's 0.006 amps here. And the cool thing is, you know they add back up together, because I2 plus I3 is equal to I1. That's 0.012 amps. That means that this one is also 0.012 amps. So you can see this is mathematically maybe a little bit more challenging, but from a standpoint of time, you don't have to break down the circuit. You don't have to do anything crazy with it to get your answers that you need. So the bottom line is, you cover the circuit with your loops, you set up your simultaneous equations, you set up your node rule, and you solve them. And it doesn't matter if it's got 10, 15, 20, or 2 or 3 loops in it, it's solvable. It's just worse math-wise, but that's about it. All right, let's take a look at one more. Might be useful. And it's a little bit different circuit than what you've seen in the past. Now, if you tried to compress this circuit, you would see very quickly that it's not so easy. You probably wonder where to go. You probably wonder how to handle 2 batteries. Don't let this freak you out. The rules are very, very clear. You have a node here. You have a node here. So what you need to do is decide what you think's going on at the nodes. How do you decide that? Go to your batteries. Go to the plus sides of the batteries. Which battery's bigger? Well, I think probably the 9 volt is bigger than the 6. Remember that voltage is like push. So it's pushing harder. So you can envision that it's causing the current. It's going to dominate and cause the current to go in the direction because it's bigger. It's winning the tug of war. So if I imagine the current coming out of here, I'm going to call this I1. And I'm going to call this I2 because it splits. And I'm going to call this I3. So now I've got my equation to start off with. I1 is equal to I2 plus I3. Cool? So there is one that we've got done. Now we've got to look at the circuit and say, okay, how many cells do you see, or how many honeycombs? I see a honeycomb here. I see a honeycomb here. Now you could strictly use the honeycombs, or you could also draw a big loop that goes all the way around it, this way. And then use one of the smaller honeycombs, and that will cover your circuit. Really, as long as you just cover the entire circuit, you're going to be fine. I'm going to change color here so you can see what I'm about to do. Oops, I'm going to change color significantly. Let's make it here, green. So let me show you what my first loop's going to be. Ready? Here we go. I'm going to call this, get a pen out. There we go. I'm going to call this, man, I'm not winning here much. Get a color. There it is. There we go. Now I got it. I'm going to call that my first loop. Okay? Bingo. So let's now use our loop rule to see what happens. I'm starting on the 9 volt battery. So 9 volts, right? As I follow it around, okay, I come to this resistor. So that equals to I2 times 15 ohms. All right? Follow my green line around. I come to here. Plus, and let me see, that means these guys split and this guy split, so they come back together. So going through this guy has got to be I1. Agreed? It's right here. It splits. There's I2. Here's I3. They come back together to make I1. So I've got plus 22 ohms times I1. Sorry, I switched my nomenclature on you. So let me clean this up. Again, I'm going to peel off all the units just so you can see the raw equation. So it's going to be 9 is equal to 22 I1 plus 15 I2. Okay, well that's pretty cool. So now I've got two equations to deal with. I've got this one and I've got this one, but I've still got that third unknown. I'm going to do something kind of strange because I want you to see this. I'm going to pick a loop that's not the honeycomb. I'm going to pick a different loop. Let's pick, and I'm going to use a color here so you can see it. I'm going to pick this loop. Watch me. I'm going to start on the 6. I'm going to go around, and I'm just going to do the complete outside. And I'm going to call that my second loop. All right? How does that change things? Well, let's see. I mean, I've purposely chosen this to make a couple of points. So here we go. I'm going to start at my 6-volt battery. So I've got 6 volts, right? Equals to. So I start to follow this around. Coming around, okay, I've got I1 times 22 ohms. Uh-oh, now I come to a battery. Now how do I deal with that? Well, it depends. That's the plus side of the battery, and this is the minus side. So I want you to think about it. If this is pushing this way, this battery is also pushing this way. So it's kind of like the flashlight rule, or it's like how you load your batteries into your calculator. You always load them in plus to minus. Plus to minus means you add them. So they make a bigger battery. They're working together. So there you would add. If you can envision, because I don't want to screw up this diagram, but if you can envision this battery here being backwards so that this side was plus, it would want to push this way, and this would want to push this way, so they would fight one another. In that case, instead of having a plus here, they would be subtracting from one another. So the polarity of the batteries, or the signs, the directions that they're working, make a huge bit of difference. All right, let's keep following our our pink line around. Got the battery, come back around. Oh, that was easy. We're done. Look how nice that was. Okay, so let's see what we've got. We've got 15 here is equal to 22 I1. Wow, look at this nice stuff. We automatically can get an answer here very quickly, right? We're going to get 15 divided by 22 is going to give us our current, right? So we've got an answer right there. And then we can take our I1, substitute it up here to find out our I2, and then we can find our I3 from there. I'm purposely not going through the math because I think you can see it. I know you're a pretty good math student. But this is how simple these circuits are. The biggest thing is keeping this sign in the appropriate direction depending upon the batteries. One other thing that this did not particularly illuminate or show you is this. If you're following one of these paths, and let's just say, and I'm going to change this, I need you to watch. Let's just say that I1 was in that direction. Well, if your loop goes against that current, then you make it negative. Okay, so that there would be a negative sign out in front of this thing instead. So you got to be careful on these signs. But outside of that, that's pretty much it on Kirchhoff's laws. Circuit analysis for that is pretty straight up. If you go onto the website and you look at some of the days that you've missed, there's a couple. I think there's 2 assignments out of the book that uses Kirchhoff's rules. So once you get kind of comfortable trying that, and there's several other problems in there that I didn't assign. If you can get me that work, we can check it out, and if there's a problem, maybe we can coordinate and see if we can't get you on the straight and narrow. Okay, I told you this would be shorter and you won't be falling asleep as quickly. Kirchhoff's law is very efficient. So, try some of these. Hopefully you feel a little bit better about those, and we'll go from there. All right.